We've all built systems that we thought were done, but how do you actually prove they're ready for production? Well, that's where system validation comes in. It's that final, absolutely critical step to make sure our game's behavior layer isn't just working, but is totally rock solid.
Let me ask you this. What's the real cost of a bug you can't reproduce? We've all been there, right? Chasing those maddening high-sin bugs, those glitches that just, poof, vanish the second you try to debug them. They burn countless hours and just completely destroy your confidence in the code. In V-Engine, we decided that cost is just unacceptable. And that's why our entire validation philosophy is built to hunt them down and eliminate them from the very start.
And this brings us to a core principle we call the reliability mandate. Look, this isn't just some goal we aim for. It's a really strict development philosophy. We believe that true reliability doesn't come from chasing bugs after the fact. It comes from a disciplined process that builds quality right in from the beginning.
And that process is what we call our spec-first workflow. It all starts with a formal design document, a spec. Then, from that spec, we write the validation tests. These tests map one-to-one with the acceptance criteria. And only then, once all the rules of the game are defined, do we actually write a single line of implementation code. The code's only job? Make those tests pass. See, validation isn't an afterthought here. It's the entire foundation.
This all leads to our ultimate mandate. It is not enough for a system to just work. It has to produce bit-identically deterministic results. What does that mean? It means the exact same inputs give you the exact same byte-for-byte output every single time on every single platform. It is a much, much higher bar, and for us, it's totally non-negotiable.
So, to even have a prayer of hitting that standard, we have to start with perfect test isolation. The #1 cause of those non-reproducible bugs is unpredictable state that bleeds over from one test into the next. We have to wipe it out.
So you really have two different ways of thinking about this. On one side, you have these test suites that use really complex fixtures or smart pointers. And they seem clever at first, but they often hide shared state, creating this messy web where one failing test can trigger a whole cascade of failures that have nothing to do with it. Our solution? It's brutally simple. We enforce patterns that guarantee every single test starts from a completely fresh, known state. No exceptions.
If you remember one thing about our testing rules, make it this. Static state is the enemy. Any piece of data that can survive between tests is a potential source of absolute chaos. We treat it like a critical threat, and we have very specific rules to get rid of it.
Okay, rule #1 is direct instantiation. Instead of messing with complex setup fixtures, we create the system object directly on the stack right inside the test case itself. This one simple move guarantees that every test gets its own brand new game state registry, the central hub for our entities and components, and starts with a totally clean slate. There's zero chance for state to carry over.
Rule #2 is the shutdown rule. In our tests, we never rely on automatic cleanup, like when a smart pointer goes out of scope. No way. Instead, every single test must call shutdown on the system it created. This forces a manual, totally predictable cleanup. It prevents resource leaks and ensures that no hidden state can possibly stick around.
All right, so with perfect isolation locked down, now we can move on to the next level. The quest for true determinism. This is where we go beyond just being correct, where the answer is basically right, to achieving bit-identical results, where the answer is mathematically identical every single time.
And here is a perfect example of why this is so tricky. You'd think the standard C++ random library would be repeatable if you give it the same seed, right? Well, you'd be wrong. The C++ standard guarantees the random generator is consistent, but not the distribution. And the result is what you see here. The same seed, 42, gives you completely different numbers on MSVC, Clang, and GCC. This makes cross-platform deterministic gameplay totally impossible.
So our solution is to just abandon the standard library for anything that touches gameplay. Instead, we use a custom deterministic RNG that's built on the PCG32 algorithm. This is the same family of generators you see in big engines like Frostbite, and it guarantees that a given seed will produce the exact same sequence of numbers, no matter the compiler, no matter the platform. Problem solved.
This brings us to the final boss, bit-identical verification. This is the ultimate proof of determinism. We're not just checking if an AI made a good move, we're proving it made the exact same move, down to the very last bit. And this is absolutely essential for things like lockstep networking and getting perfectly stable gameplay replays. So, how do we actually prove it? We use a tool we built called the InputHarness.
It lets us inject a super precise, scripted sequence of inputs into the engine, frame by frame. We run the simulation and generate a telemetry log. Then we do it again, run the exact same simulation and generate a second log. Finally, we diff the two files. The goal is a perfect match. A diff 0 is victory. It means we've achieved true bit-identical determinism.
So let's bring this all together. These patterns, these rules, they aren't just arbitrary. They form the very foundation for building stable, complex gameplay. And trust me, this disciplined approach has a massive payoff.
Here's the checklist that really sums up our entire strategy. We get isolated state by using direct instantiation, we enforce a clean exit with the shutdown rule, and we prove our most complex systems are perfectly reproducible using the input harness and our deterministic RNG. It's that simple.
And what do you get for all this discipline? Confidence. That's what it is. It's the confidence of knowing your game's behavior layer is stable, it's reliable, and it's truly production ready. It gives you the freedom to build amazing, complex features right on top of this foundation, without ever worrying about those subtle, nightmarish bugs coming back to haunt you.
And that really leaves us with one final critical question. As games get more and more complex with networking, replays, crazy sophisticated AI, the demand for this kind of reliability is only going up. So you have to ask yourself, is your testing philosophy built to actually withstand that complexity?